Welcome students once again into the class of number theory, and today in this class, in this video, we will state and prove Chinese remainder theorem to solve a system of linear congruences, and then I'll try to give one example as well. So let us first of all see what Chinese remainder theorem is. So it is Chinese remainder theorem. So let us see what it says, and then we'll give an example. The theorem says let M1, M2 and so on Mn be positive integers relatively prime to each other, or you can say relatively prime in pairs, then for any integers a1, a2 and so on an, the system of linear congruences, like x1 is congruent to a1 mod m1, x is congruent to a2 mod m2 and so on, x is congruent to an mod mn, has exactly one solution modulo m, where what is m? Here m is m1, m2, m3 and so on, m and their product. So this is the statement of the Chinese remainder theorem. First we will prove this theorem, and then I'll tell you how to solve questions using this Chinese remainder theorem. So let us first discuss the proof of Chinese remainder theorem. So what we are given with? We are given with a system of linear congruences, and these linear congruences are x is congruent to a1 mod m1, comma, x is congruent to a2 mod m2 and so on, x is congruent to an mod mn. This is given to you. Where what these m1, m2, mn are? These are integers, positive integers, which are relatively prime to each other in pairs. For example, you can have 2, 3, 5 and one of them you can have 49. 49 itself is not a prime, but they are relatively prime in pairs. GCD of 2 and 3 is 1, GCD of 2 and 5 is 1, GCD of 2 and 49 is 1, GCD of 3 and 5 is 1, GCD of 3 and 49 is 1, GCD of 5 and 49 is 1, so they are relatively prime in pairs. So M1, M2, Mn are relatively prime in pairs. So you can even take 4, 9, 25. None of these is a prime, but they are relatively prime in pairs. So this type of integers M1, M2, Mn are. So this system of linear congruences is given to us. And what is your M? Your M is the product of these integers m1, m2, m3 and mn. Now define capital Mk as m divided by small mk. That means what is your capital M1? It is small m divided by small m1. And when you will divide this m by small m1, m1 will be cancelled out and rest of all the numbers will be there in the product, m2, m3 and so on, mn. Similarly, in capital M2 you will not have small m2, but you will have product of rest of small mi's. Similarly, in mk you will have the product of all small mi's leaving small mk, and this is this is how we are defining this mk. So after defining mk, one thing you must note, we are given that these mi's, they are relatively prime in pairs. That means you take any two mi's, mi and mj, then their GCD is 1 if I is not equal to j. Why? Because they are relatively prime in pairs. So that means if you take GCD of mi with this product m1, m2 and so on, mi minus 1, mi plus 1 and so on up to mn, the GCD will still be 1, because GCD of mi m1 is 1, GCD of mi m2 is 1, GCD of mi minus 1 is 1, GCD of mi plus 1 is 1, GCD of mi mn is 1. So GCD of mi with the product of these numbers is also 1. But what this number is, in this product you are having all mi's other than particular small mi. So that means this is your capital Mi. This is your capital Mi. So in short, you can say that defining Mk like this, you will get GCD of capital Mk and small mk is 1. And one thing also is to be noted, that this Mk is congruent to 0 modulo Mi if your I is not equal to k. Because in this Mk, you are having a product of small mi's. The particular small mk is not there, but all mi's are there. So if you are taking some other I other than k, then small mi will divide the product. And the product minus 0 is the product itself. So mk will be congruent to 0 modulo mi. These two are very, very clear. Another thing, that this mk and small mk, the GCD is 1. So definitely there exist some integers, you can say yk and bk. First I am writing some integers bk and yk such that these are integers such that mk bk plus small mk yk is equal to 1. Why? Because you know that if GCD of two numbers is d, then there is a linear combination of these two integers which gives the result equal to the greatest common divisor. So if GCD of a and b is 1, then definitely there will be a linear combination of a and b which will be equal to 1. From here, if you take this 1 to the left hand side, so it will become minus 1, and to the right hand side you will get minus mk yk, or in other terms you can say that mk, small mk, divides capital Mk bk minus 1, or in other words you can say that your capital Mk bk is congruent to 1 modulo small mk. There will definitely be a solution bk to this congruence equation. So we are having this relation. Now define, let x naught be an integer equal to a1 capital M1 b1 plus a2 capital M2 b2 plus and so on plus an capital Mn bn. If you consider this equation, you know that mk is congruent to 0 modulo mi if I is not equal to k. If mk is congruent to 0, then multiplying this mk by ak bk, this will also be congruent to 0 modulo mi if I is not equal to k. So if you are taking, these two numbers are equal, and you know that the congruence relation is reflexive relation. So these two numbers are equal, that means they are congruent to each other modulo anything, and here I am taking modulo mi, say modulo mi. Now when I is not equal to k, this quantity A1, M1, B1, A2, M2, B2, like this quantity, they will become congruent to 0 when I is not equal to k. So what you will be left with? You will left with the only one term that will contain ai, mi, bi, because all the others will have k not equal to I, and this quantity will become congruent to 0. So 0, 0, 0, and you will be left with only one quantity, that is ai, mi, bi modulo mi. Another thing, your mk bk is congruent to 1 modulo mk for every k. So this mi bi is congruent to 1 modulo mi. So this mi bi is going to be congruent to 1, and you will be left with congruent to ai modulo mi. And this is true for all I. For all I equal to 1, 2, 3, 4 and so on up to n. So that means x naught satisfies x congruent to a1 modulo m1, x congruent to a2 modulo m2, x congruent to a3 modulo m3, and so on, x congruent to an modulo m1. That means this x naught is a solution to all these congruence equations. So that means x naught is a solution to this system of linear equations, linear congruence equations. X naught is a solution, but the question is, solutions should be unique. Now we are moving towards uniqueness, because we have proved the existence of the solution. The solution will exist. And what the solution will be? Solution will be x naught equal to a1 m1 b1, a2 m2 b2, a3 m3 b3, and so on, an mn bn. This will be the solution. And now we are moving towards the uniqueness. So suppose there be two solutions, x naught and y naught. So that means x naught is congruent to ai modulo mi for every I, and y naught is also congruent to ai modulo mi for every I. And the congruence relation is a transitive relation. X naught is congruent to ai and ai is congruent to x naught. That means x naught is congruent to y naught. So x naught is congruent to y naught modulo mi for every I. Note that this x naught is coming out to be congruent to y naught for every mi. And you know that these mi's are relatively prime in pair. So x naught will be congruent to y naught modulo product of these mi's, m1, m2, m3 and so on, mn, because they are relatively prime to each other. And what this product is? This product is m. So your x naught is congruent to y naught modulo m. That means modulo m, you are having a unique solution. If any other solution is there, that will be congruent to x naught modulo m. So you are having a unique solution. So we have proved Chinese remainder theorem. That means a system of linear congruence equations with m1, m2 and so on, mn as relatively prime in pairs, and for every i's you are having a unique solution modulo m, where m is the product of all these mi's. And now look at one example. Let us have one example. So consider these equations. X is congruent to 1 modulo 2, x is congruent to 2 modulo 5, x is congruent to 4 modulo 7. It seems that the solution will be very easy to find by hit and trial, but it is not so easy. This question actually what it dictates, x is a number which when divided by 2 gives remainder 1, when divided by 5 gives remainder 2, and when divided by 7 gives remainder 4. What this number x is, which satisfies this property. So it looks that the solution will be easy, can be obtained by using hit and trial, but it is not so easy. When you solve it, the solution will find, and you will look that the solution cannot be easily obtained by hit and trial. So what are your a1, a2, a3 and m1, m2, m3 here? Here your a1 is 1, this one, your a2 is 2, this 2, your a3 is 4, this 4, your m1 is 2, this 2, your M2 is 5, this 5, and your M3 is 7, this 7. So what is your capital M1? Your capital M1 is M2 into M3, 5 into 7, so it is 35. Similarly, your capital M2 is M1 into M3, 2 into 7 is 14, and your capital M3 is M1 into M2, 2 into 5 is 10. Now, consider these equations. M1 x is congruent to 1 modulo small m1. M2x is congruent to 1 modulo small m2. And M3x is congruent to 1 modulo small m3. Consider these equations and substitute the values what you know. What is your M1? Your M1 is 35. So this is your 35. This M2 is 14. This M3 is 10. This small m1 is 2. Small m2 is 5. And small m3 is 7. Now these equations will have a unique solution, and that solution for the first equation will be b1, for the second one it will be b2, and for the third one it will be b3. But let us make it more simpler, more easier. Divide this 35 by 2, and what the remainder you are going to get is 1. So you can replace this 35 by 1. So it is x congruent to 1 modulo 2. Here this is 14. Divide this 14 by 5, and what the remainder you are going to obtain is 4. So you can replace this 14 by 4. And divide this 10 by 7, the remainder obtained will be 3. So this 10 can be replaced by 3. And now here use your hit and trial method. Hit and trial method to find the, I am writing M1 was 35, M2 was 14, M3 was 10. Now, look into the first equation. Which integer satisfy the first congruence equation? It is simply, you can say 1. So, 1 is a solution to the first one. So, 1 is the value of B1. So, your B1 is 1. The solution of second will be B2. Which number x satisfies this equation? If you take 1, it will not be satisfied. 2 will not be satisfied. 3, no solution. 4 is a solution because 4 into 4 is 16, and 16 minus 1, 15 is divisible by 5. So the solution is 4. That means your B2 is 4. Similarly, try to find this B3. For x is equal to 1, no solution. 2, no. 3, no. 5 will be the solution because 3 into 5, 15. 15 minus 1, 14 is divisible by 7. So your B3 is 5. Now your final solution x0 is A1 M1 B1 plus A2 M2 B2 plus A3 M3 B3 modulo M. Now look at just simple calculation work remains now. A1 into M1 into B1. So it is 1 into 35 into 1 is 35. So the first quantity is going to be equal to 35 plus A2 M2 B2. 2 multiplied by 14 is 28, and 28 multiplied by 4 is 112 plus A3 M3 B3. 4 into 10 is 40, and 40 multiplied by 5 is 200. But this number is not the simple solution, it is solution congruent modulo M, and your M is the product of all these three MIs. 2 into 5 into 7 is 70. So this is x0 is congruent to, now add these all. 112 plus 35 is 147 plus 200 is 347 modulo 70. So to make the number easier, or you can say to find the smallest least positive solution, divide this 347 by 70 and replace the 347 by the remainder. So what the remainder will be? If you divide 347 by 70, the remainder will be 67. So 67 modulo 70. This is the unique solution of this system of linear congruences. If you divide 67 by 2, the remainder will be 1. If you divide 67 by 5, the remainder will be 2. And if you divide 67 by 7, the remainder will be 4. So this is how we can prove Chinese remainder theorem, and we can solve systems of linear congruence equations by using Chinese remainder theorem. So in the next video, I'll take more and more examples. Till then, thank you. Thank you once again.